Hi everyone, welcome back to my video about programming with Go. I am Dr. Hang Ding from Indiana University South Bend. In this video, we will cover part 2 of topic 1.3, composite types. And the topics that we focus on is arrays and slices in Golang. Let's start with arrays. Recall that array is a data type that represents a list of values of the same type. In Golang, the syntax to specify an array data type starts with the array size enclosed in square brackets and followed by the data type of the array elements. So the type n in brackets t is an array of n values of time t. For example, 10 in brackets, then int, is the data type for an array of 10 integers. And you can declare a variable of this array type just like the way you declare any variable. The statement var a 10 int declares a variable a as an array of 10 integers. Note that the length of an array is part of the array type, so arrays cannot be resized. For example, after declaring a as an array of 10 integers, then array a will always have 10 elements. Here is a fragment of code that shows more examples of arrays in Golang. In the first part of this code fragment, we declare variable a as an array of 2 strings. Then we assign the first element of array a to string hello and assign the second one to the here we assign the first element of the array a to the string hello, and we assign the second element of array a to the string word. Recall that in any language, in Golang and also in several other languages, to access an element of an array, we use the syntax that starts with the array name and then followed by the open brackets, then the index, then the close bracket. And the index of an array always starts with 0. So A0 indicates the first element of the array A, and A1 indicates the second element of the array A. The first println statement in this code will print out the first 2 elements of the array A as the 2 strings. And the second println statement will print out the entire array A. And as you can see in the output, when it prints out the entire array, it will display the square brackets as well. And in the second part of this code fragment, we declare and initialize the variable primes to be an array of 6 integers. And here we also initialize the first 4 elements of the array primes to have the value 2, 3, 5, 7. So in general, you can initialize an array of size n by providing up to n values. And if you provide fewer than the size of the array, then the remaining elements of the array will receive the 0 values of the element type. Recall that an array has a fixed size, so it's not flexible. Golang has another data type known as slice, which is a dynamically sized flexible view into the elements of an array. In practice, slices are much more common than arrays. The syntax to specify a slice data type is the same as array data type, but without specifying the size. So we just write open brackets, close brackets, followed by a type t to indicate a slice with elements of time t. For example, the expression open brackets, close brackets, int is the data type of a slice with elements of type int. A slice is formed by specifying a low index and a high index of an array, as in this expression, which starts with the array name followed by an open bracket, then the low index, then a colon, then the high index, and ended with a close bracket. This expression selects a half-open range including the first element, but excluding the last element of the range. So it includes the elements of the array from index low to index high minus 1. For example, in this code fragment, we have declared and created the array named primes, which has 6 elements of time int, and here are the values of the elements of the array of primes. And then in the second line of code, we declare a variable s of the slice data type, which is a slice of elements of time int. Okay? And then we initialize the slice s to be the range of the array primes from the low index of 1 to the high index of 4. And if we print out the value of the slice s, then we only see the elements of the arrays primes from index 1 to index 3. So those elements are 3, 5, and 7. It does not include the element at index 4, which is 11. The best way to view slices is that they are like references to arrays. It means that a slice does not store any data. It just describes a section of an underlying array. So changing elements of a slice will modify the corresponding elements of its underlying array. And other slices that share the same underlying array will see those changes. This code fragment is an example demonstrating these effects of changing elements of a slice. In this code fragment, we first declare variable names as an array of 4 strings and initialize those 4 strings to be the 4 names John, Paul, George, and Ringo. The list of those 4 strings is shown when the array names is printed out in the second line of code. Then we declare 2 slices A and B from array names. Slice A specifies the half-open range of array names from index 0 to index 2. So it includes 2 elements, John and Paul, corresponding to the elements at index 0 and 1 of array names. Slice B specifies the half-open range of array names from index 1 to index 3. So it includes 2 elements, Paul and George of array names. Then we change element at index 0 of slide B to be the string XXX. Note that the element at index 0 of slide B corresponds to the element at index 1 of array names. So before changing, that element has value pause. After changing the element B0, the element at index 1 of the underlying array names is also changed to XXX, as is showed when we print out the array names after changing B0 to XXX. Also, since the second element of the slice A shares the same element at index 1 of array names, slide A also sees this change from pause to XXX. When we use arrays, we can create array littles. For example, this is an array little, which is an array of 3 bool values true to false. Similarly, when we use slices, we can create slice littles. A slice little is like an array little, but without the length. For example, if we remove the length 3 from this array little, we have a slice little. This expression creates the same array little as above, then builds a slice that references that underlying array. For a more complex example, let's consider this code fragment. The first line of code creates a slice little named Q that references an unnamed array of 6 integers with values 2, 3, 5, 7, 11, and 13. Then it prints out the slice Q. Next, it creates another slice little r that references an array of 4 Boolean values, true, false, true, true. Then it also prints out the slice r. The third slice little named S in this code fragment is a slice of struct. This struct has 2 fields, namely I of time int and b of time bool. So each value of this struct or each struct little of this struct is written as a pair of an integer and a bool value enclosed in braces. To make the list of struct values readable, we can write one struct value per line, like this one. But note that if you place the closing brace of the list in a separate line, like this one, then you need to add a comma after the last value in the list. Let's test this code fragment on the Go playground. So let's run it, and okay, so and here is the output. Okay, so this is the slide little Q, and this is the slice little r, and the last line of the output is the slice little s. Okay, so now if we remove this comma, and so we try to run it again, you see that it shows an error. Okay, syntax error. So to fix that, you must either add a comma here, or you have to put the closing brace of the list on the same line as the last value in the list, like this one. So now when we run it, it works again. When slicing, you may omit the high or low bounds to use their default instead. The default low bound of a slice is always 0. The default high bound is the length of the slice. For example, given the array A of 10 int, these slice expressions are equivalent. They are all referencing the array A from index 0 to the index 10, and but excluding the index 10. Right? So in the second one here, if we omit the low bound, so it's the same as using the low bound of 0. And in the third one here, when we omit the high bound, then it's the same as using the length of the array, which is 10, as the default value. And you can also omit both the low bound and the high bound. So in this case, it's the same as referring to the entire array. And so here is a more complex example. And in this example, we have the slice S with 6 integers. And so now you can also slicing from another slice. And so we define S to be S from 1 to 4. So in this case, it is reslicing S as the value from so that it contains only the value from index 1 up to index, so from index 1 here up to index 3. Okay, it doesn't include the one at index 4. So when you print it out, it shows 3, 5, 7, which are the elements from index 1 to 3 of the original slice. Right? And then so now you slicing S again. So in this case, it's the same as S from 0 to 2. And so that means that you just take the one at index 0 and the one at index 1. So that is from the current slice S. So that is from this one. So therefore, when you print it out, it only show the first two elements, which are 3 and 5. Okay, so now after this line of code, the slide S just contains only two elements, 3 and 5. And so now when we slice S again from 1, okay, and then we omit the high bound, so the same as slicing the slice S from index 1 up to the end of the slice. And so it includes only the last element here, so that is 5. Another difference between slice and array is that a slice has both a length and a capacity, while an array has only a length. The length of a slice is the number of elements it contains. The capacity of a slice is the number of elements in the underlying array, counting from the first element in the slice to the end of the underlying array. The length and capacity of a slice S can be obtained using the expression length of S and cap of S respectively, as in the following examples. Here we first declare variable S to be a slice literal consisting of 6 integers. Okay, so this is the slice S after being graded. Then we print out the length the length of S and the capacity of S in the first println statement. It shows that both the length of S and the capacity of S are 6 because the underlying array of the slice literal has 6 elements and the slice literal includes all of them. The length and capacity of a slice can be changed by reslicing, that is, specifying a new low bound and a high low bound of the slice itself. For example, when we reslice S with the new bounds of 1 to 4, the new slice will have only 3 elements from index 1 to index 3 of the old slice. The capacity of the new slice is reduced by 1 from 6 to 5 because the first element of the new slice is now at index 1 of the underlying array. The element at index 0 of the underlying array is not counted toward the capacity of the new slice. In general, by reslicing a slice, you can reduce its length and/or its capacity, and you can also extend its length provided it has sufficient capacity, but you cannot extend its capacity. The new capacity always equals the old capacity minus the new low bound. So if the new low bound is positive, the slice capacity will be reduced, otherwise it's unchanged. For example, consider the slice S graded from the slice literal of 6 integers, as in the previous example, and as explained before, its initial length and initial capacity are both equal to 6. After reslicing S with the high bound of 0, its length is reduced to 0 because there's no element of index less than 0. However, its capacity is unchanged because in this reslicing, the new low bound, which is on the left of the colon, is 0 by default. Then we reslice S with the low bound of 2 and the high bound of 5. This reslicing reduces its capacity by 2 because the new low bound is 2. So the new capacity equals 6 minus 2, which is 4. This reslicing also extends its length from 0 to 3 because now there are 3 elements in the slice from index 2 to index 4 of the underlying array. Then we reslice S with the high bound of 4 and the default low bound of 0. This doesn't change its capacity because the new low bound is 0. The new capacity is still 4. But this reslicing extends the length of the slice from 3 to 4 because there are 4 elements in the half range from index 0 to index 4. Note that when reslicing, index 0 corresponds to the first element of the current slice, not the first element of the underlying array. And the first element of the current slice is at index 2 of the underlying array. So the resulting slice after reslicing consisting of the four elements from index 2 of the underlying array instead of from index 0 of the underlying array. An example of where slices are used is in command line arguments. Command line arguments for a program are stored in a variable os.args, which is a slice of strings. This variable is defined in the standard package OS, which provides functions and other values for dealing with the operating system in a platform-independent fashion. The first element of the slice os.args, which is an index 0, stores the name of the command or program itself. For example, when we run this program named echo1.go from the command line, then os.args at 0 is the string echo1. This program implements the Unix echo command by simply printing out all elements of the slice os.args from index 1. The element at index 1 stores the first argument of the program. The element at index 2 stores the second argument of the program, and so on. A slide can have the 0 value, which is called nil. A nil slide has both length and capacity of 0 and has no underlying array. When you declare a slice variable, then that slice variable is a nil slide. For example, in this program, after declaring variable s as a slice of int, then s is a nil slice. When we print out the slice s, its length and its capacity, it displays just the empty slice and zeros for both length and capacity. Then this program also compares if s equals nil, and if it is, then it prints out the string nils exclamation point. And in the output, it displays nils exclamation point. This confirms that S is a nil slice. In previous examples, we showed how to create a slice from an array whose size is unchanged. Now you will learn another way to create a slice, that is to use the built-in make function. This is also how you create dynamically sized arrays. Dynamically sized arrays are those whose size are not determined by a constant but can be determined by a variable. When calling the make function, you have to specify the slice type in the first argument and a length in the second argument. The make function then allocates a zeroed array with the given length and returns a slice that refers to that array. So in this case, the slice capacity equals to is equal to its length. For example, the call to function make with open square and close open square brackets and close square brackets int in the first argument and 5 in the second argument returns a slice of 5 zero integers with capacity with the length 5 and also the capacity 5. To specify a capacity that is different from the initial length, you can pass a third argument to the make function. For example, the statement b colon equal make of open square brackets, close square brackets, int, comma, 0, comma, 5 will create slice B of integers with 0 length and capacity 5. Then you can reslice B to increase its length to match its capacity of 5. Then you can reslice B again to reduce its capacity and length down to 4. Slices can contain any type, including other slices. Here is an example of a slice of slices. In this program, we create a slice board to represent a tic-tac-toe board of 3 rows and 3 columns. Each row is a slice of 3 strings corresponding to 3 columns, where each string consists of a single character that represents a cell in the board. An underscore character represents an empty cell. The slice board contains 3 slices representing the 3 rows. So the type of a slice board is written as a pair of open and close square brackets, and then another pair of an open and close square brackets, and then string. To access each cell in the board, we specify 2 indexes. The first index indicates the row index, and the second index indicates the column index. For example, board 1, 0 refers to the cell in row 1 and column 0. Board 0, 0 and board 0, 2 refer to the first and the last cells in the first row, which has index 0. These 3 assignment statements change the content of those 3 cells according to how the players play. The for loop in this program displays the content of the board after the changes. It is common to append new elements to a slice, so Go provides a built-in append function. This is how the append function is declared. The first argument of the append function is a slice, and the remaining arguments are the values to append to the slice. Those values must have the same type as the element type of the slice given in the first argument. The resulting value of the append function is a slice containing all the elements of the original slice plus the provided values. If the backing array of the given slice is too small to fit all the given values, then a bigger array will be allocated, and the returned slice will point to the newly allocated array. This code fragment shows examples of appending to a slice. It starts with declaring variable s as a slice of time int. So s is a new slice initially. Then it displays the content of a slice s along with its length and capacity by calling the print slice function, which is defined here. The first call to function append demonstrates that the append function works on new slice as well. This function calls as the value 0 to the new slice S, creating a new slice that has one element. The assignment makes S refers to the new slice. After this assignment statement, slice S has length 1 and capacity 1, and its only element has a value 0. The second call to the append function as another value, which is integer 1, to slice S. So after this appending, slice S has length 2 and capacity 2, and its elements are 0 and 1. The last call to the append function is an example of adding more than one element at a time. This function calls as three values 2, 3, 4 to slice S. After adding, the length of S increases from 2 to 5. However, this example also shows that the new capacity is not always equal to the new length. Here the capacity is increased from 2 to 6 instead of 5. The algorithm to determine the new capacity after appending is an implementation detail of Go runtime and can evolve. We don't need to know such a detail, but in essence, Go's append function aims to balance efficient memory usage with minimizing frequent relocations. It grows the underlying array in a way that provides room for future appends without excessive overhead. Finally, let's compare between strings and byte slices because these are popular data types. Both strings and byte slices are sequences of bytes, but byte slices are mutable, that is, they can be changed, while strings are not. The standard package byte has similar functions for manipulating byte slices. Since strings are not mutable, building up strings incrementally can involve a lot of allocation and copying. In such cases, it's more efficient to use bytes.buffer type, which is defined in package bytes. You can convert between strings and byte slices by using explicit type conversion. For example, suppose S is a string containing the sequence of characters ABC. Then this statement converts string S to a byte slice referred to by variable B. And this statement converts the byte slice B back to a string referred to by variable S2, which should have the same content as string S. Okay, so that's all about slices and arrays in Golang. Thank you for watching and hope to see you again in the next video.